This video is entitled Transformer Fundamentals, and it is covering the basic formulas or the basic equations that are associated with a power transformer. And indeed, it's actually the same formulas that are used in any type of transformer, whether it's a power transformer or an electrical transformer or electronic transformer. They all have the basic same formulas. It covers, as I said, the basic formulas, the basic understandings of an ideal transformer. For further information, I encourage you to check into my website, which will have the various idiosyncrasies of three-phase transformers, three-phase connections such as Y delta, delta Y, Y zigzag type transformers. It'll also host a series of other courses that go from the very basic to the more exotic subject matters that are associated with transformers. So I encourage you to check into my website, getpspt.com, and you'll be instructed how to go about streaming the various videos there. Transformers are commonly used in applications which require conversion of AC voltage from one voltage level to another. There are two broad categories of transformers: electronic transformers, which operate at a very low power and are used for consumer electronic equipment such as television sets, VCRs, CDs, personal computers, and many other devices to reduce the level of the voltage from 110 and 220, which is available at the AC mains, to the desired level at which the device operates. The other category of transformer is power transformers, which process thousands of watts of power. Power transformers are used in power stations, transmission and distribution systems to raise and lower the level of the voltage to the desired levels. The basic principles of operation of both of these types of transformers are the same. The transformer fundamentals we're going to talk about in the next few slides apply to both the electronic transformer and the power transformer. Before diving into the inner workings of a transformer, let's back up a couple of paces and review electromagnetism first. In electromagnetism, there is a magnetic field that is produced by an electric current flowing in a wire. Now, remember, we can't see these fields and we can't feel them, but we can observe their effect on other magnetic fields and other things. And the magnetic field produced by a current flowing in a wire is perpendicular to the wire and is imagined to form rings around the wire itself as current is flowing in it. The direction of the magnetic lines of flux are given by what we call the right-hand rule. If we place our right hand on the conductor and your thumb is pointed in the direction of the current flow, then the magnetic field forms concentric circles in the direction of your fingers, as demonstrated in the diagram here. And as I said, the magnetic field encircles the wire, and the flux lines have no north or south pole. They are continuous lines of flux that are formed around the wire. So far we've been banting about the terms of flux, the lines of flux and the force fields, and that's been okay up to now when we're only dealing with singularity things and haven't talked about formulas, but we need to define them in quantitative terms, which we're going to do here, so that we can go forward and develop formulas for use in electromagnetic fields. When analyzing magnetic fields, we need to further define them as being made up of magnetic lines of flux And a flux line is demonstrated here, and it's, again, we can't see them, but we can imagine them going through a particular surface. Grouped together, these magnetic lines of flux form what is known as a magnetic flux field, and the Greek symbol phi is usually used to symbolize magnetic flux field. And it's a measure of quantity of magnetism. It takes into account the strength and the extent of the magnetic field. If we consider a flat area, such as what is in yellow there, that the magnetic flux passes through, then we can define magnetic flux density as the amount of magnetic flux in an area that is perpendicular to the direction of the magnetic flux. Or in other words, magnetic flux density is the amount of magnetic flux perpendicular to a given flat surface area divided by that area. And it's usually defined by the capital Greek letter beta, but beta is very close to our capital letter B, so quite often you'll just see the letter B as designating flux density. And the international symbol used for measuring the quantity of flux density is the Tesla. And 1 Tesla is equal to 1 Weber per meter per square meter. And quite often we don't use the term Tesla. Quite often we're just going to use the term Weber per square meter, and you'll see that happening often. So to summarize, here's what we'll be using going forward for discussing magnetic flux and magnetic flux density. Magnetic flux is usually symbolized by the Greek letter phi, and it's usually measured in Webers. Magnetic flux density is B or beta, and it's measured in Tesla, which is equivalent to Webers per square meter. To create a stronger magnetic field force and consequently more field flux with the same amount of electric current, we can wrap the wire into a coil shape where the circling magnetic fields around the wire join together to create a larger field with a defined magnetic north and south pole polarity. The amount of magnetic field force generated by the coiled wire is proportional to the current through the wire, multiplied by the number of turns or wraps of that coil wire. The more wraps, the more turns, the larger the magnetic field that will be produced. This force field is called magnemotive force, MMF, and is very much analogous to electromotive force, which is voltage, in an electric circuit. MMF is measured in ampere turns. The poles of a magnetic field in a coil of wire or a solenoid, which is called, can be determined again by the right-hand rule. Imagine your right hand gripping the coil of the solenoid such that your fingers are pointing in the same way that the current is flowing. Your thumb then points in the direction of the field. Since the magnetic field is always coming out from the North Pole, therefore the thumb points towards the North Pole. Here we have wrapped our coil around a block of iron, which I will refer to as core material. The nature of this material is such that the magnetic lines of flux want to travel through it rather than the air. In fact, it will boost the amount of flux that is produced by the current in the coil. In this example, the magnetic flux will still vary as the current in the coil, but at a greater extent due to the core material. The magnitude of the magnetic flux will also depend on the number of turns of the coil. As I said, the magnitude of magnetic flux will also depend on the material through which the flux will travel. If an iron core is substituted for an air core in a given coil, the magnitude of magnetic field is greatly increased. All materials have a property defined as permeability, which is the measure of the ability of the material to support the formation of a magnetic field within itself. Hence, it is a degree of magnetization that a material obtains in response to an applied magnetic field. Magnetic permeability is typically represented by the Greek letter mu. Permeability, also called magnetic permeability, is a constant of proportionality that exists between magnetic induction due to the current flow and the magnetic field intensity, or the amount of flux that will be produced. This constant is equal to approximately 1.257 times 10 to the negative 6 henries per meter in free space, or a vacuum. In other materials, it can be much different, often substantially greater than in free space, which is symbolized by the Greek letter mu with a subscript 0. Materials that cause lines of flux to move farther apart, resulting in a decreased amount of magnetic flux density compared to a vacuum, are called diamagnetic materials. Materials that concentrate the magnetic flux by a factor of more than 1 but less than or equal to 10 are called paramagnetic materials. And most importantly, the materials that concentrate the flux by a factor of more than 10 are called ferromagnetic. The permeability factors of some substances change with the rising and falling of temperatures or the intensity of the applied magnetic field. In engineering applications, permeability is often expressed in relative rather than absolute terms. If mu subscript 0, or we call it mu naught, represents the permeability of free space, and mu represents the permeability of the substance in question, then the relative permeability, mu subscript r, is given by this equation. The permeability of material and its capability of either supporting or resisting a magnetic field is called reluctance or magnetic resistance. The reluctance of a magnetic material is proportional to the mean length of that material and inversely proportional to the cross-sectional area, and of course the permeability of the magnetic material itself. It gives rise to the equation R is equal to L over mu A, where R is the reluctance or magnetic resistance of the material, mu is the magnetic permeability coefficient, L is the length of the material in meters, and A is the cross-sectional area of that material in square meters. So looking at our coil again on our block of iron, the iron is a ferromagnetic material and it's said to have a reluctance R to the flux that is being formed by the current. The flux, current, and reluctance are related by this equation. Ni is equal to the flux times the reluctance. So if we increase the current, we're going to increase the amount of flux. If we increase the turns, we're going to increase the amount of flux. If the reluctance goes up for the same amount of current and turns, then the flux density would have to go down. So the reluctance actually provides some resistance to the formation of magnetic flux lines in the iron core. Remember now that the Ni is termed magnemotive force, or MMF, and it's measured in ampere turns. The next thing we want to review is something called Faraday's law. And Michael Faraday discovered that whenever a conductor is moved through a magnetic field, or whenever a magnetic field near a conductor is changed, current flows in that conductor. And this effect is called electromagnetic induction. And through observation and study, he discovered that the voltage induced in each coil of that wrapped coil, in each loop of that coil, I should say, is given by the equation E, where E is the voltage that's induced, is equal to minus d phi by dt. Now, d phi by dt, it just means the change in flux over a period of time. So really, it's whatever the field changed from time 2 to time 1, that's the voltage that would be induced in that loop of wire. And if you wrap 10 turns in the way of a coil, then you have to multiply that voltage by 10, because each loop will have the same induction, the same voltage induced in it. So it would be a series of voltages connected together. So you have to multiply by the number of turns of that coil. So the voltage that you see on the meter is being read by the number of turns in the coil times the change in the magnetic flux over a period of time. Before proceeding, I want to emphasize an important concept to remember. Flux and flux density and the related current are always proportional. And this is regardless of whether that current is AC or DC. When flux and flux density are zero, the related current is zero. When flux and flux density are at a maximum, the related current is at a maximum. And when the flux and flux density are at a minimum, the related current is at a minimum. So if we're talking about AC quantities, the flux field is in phase with the current. Or you might say the reverse of that is the current is in phase with the flux field. As it changes, so does the current. If we wind two coils on a steel core, we can cause almost all of the flux to be linked by both coils. And we can further hypothesize that the case in which 100% of the flux is linked. In this case, it is called an ideal transformer. In coil 1, the flux produced by the generator is related to the voltage by Faraday's law. And if that voltage is changing, as in the case of AC volts, then the voltage will be given by the number of turns of the coil in the red coil times the changing magnetic flux over a period of time. And we'll say let that voltage in terms of AC quantities be V1. In coil 2, the voltage produced by the linked flux by mutual inductance is also given by Faraday law. And since it's the same amount of flux, because we said that in an ideal transformer you had 100% linkages, then the voltage produced, V2, is going to be also equal to minus N2 d phi by dt. So we know that the changing magnetic flux field d phi by dt is the same for both of them. So you can say that changing these equations around, that d phi by dt is equal to v1 over n1, which is equal to v2 over n2. Or you can say v1 over n1 is equal to v2 over n2. Or v1 over v2 is equal to n1 over n2. So this ratio, n1 to n2, is known as the turns ratio of the transformer. It can also be designated by the primary voltage over the secondary voltage. They're both equal, so they both are a measure of the turns ratio of the transformer. Let's take a closer look at the Faraday equation and its relationship to, say, a coil on a magnetic core. What this equation states, and Faraday states, I guess, is that there's a relationship between the voltage across the coil and the magnetic flux in the core. The instantaneous voltage, that is the voltage drop at any instant of time across the wire coil, is equal to the number of turns of that coil around the core multiplied by the instantaneous rate of change of magnetic flux. And that's the term d phi by dt. That's just describing the rate of change of the magnetic flux linking the coil. This describes the relationship of the flux and the voltage. For example, if there is a sinusoidal flux present in the core, the voltage would be designated by Faraday's equation, and if each point on this sinusoidal wave were calculated and plotted, it would look like this. A sine wave, which is shown in blue, that is 1/4 of a wavelength, or 90 degrees, in front of the flux wave, or you might say the flux wave lags the voltage wave by 90 degrees. Magnetic flux lags applied voltage by 90 degrees because the voltage E is proportional to the rate of change of flux d phi by dt. So if we start to examine these two wave shapes, what this says is when the flux change is 0, which is at the maximum and the minimum waveform for the magnetic flux, the magnetic flux is changing at a 0 rate at these points. And if it's changing at a 0 rate, then the voltage must be 0 at that point. And yes, indeed, the blue sinusoidal waveform is 0 exactly at those points. And when the magnetic flux is at a maximum rate of change, which is where it crosses, is the 0 crossing of the black line there, that is when the magnetic flux is at its maximum change. Then that's when the voltages will be at their maximum. Here is an important concept that tends to get muddled, at least it did for me. Let's consider an iron core with 2 coils wrapped on it. This essentially is a 2-winding transformer. If we apply an AC voltage to the primary, the flux developed is related to the voltage by Faraday's equation. So we would say that the voltage V1 across the primary coil is equal to minus N1, which is the turns of that coil, times the changing magnetic flux. By mutual inductance, an AC voltage is induced in the secondary, which is related to the same flux developed by the primary voltage, and this voltage is given by the equation E equal minus N2, which is the turns of the secondary coil, times the changing flux, which is equal to V2. We have to keep in mind, though, that there is current flowing somewhere in order to be producing or related to the flux present, and that current is coming from I1, which is in the primary coil. So if there is a flux present, which there must be in order for mutual inductance to occur, then I1 must be greater than 0, even if the secondary is open circuited. This is an important concept in transformers, and that there is some current always present, albeit small, and it must flow in the primary in order to magnetize the transformer. This is called magnetization current, and it is small, but it is present in the secondary open circuit of a transformer. Once the secondary is loaded, I2 starts to flow and the flux will increase with the load current. And I2 will be determined by the impedance or the resistance of the load. The smaller the resistance, the more current will flow. If the secondary current is allowed to increase unrestricted, it will drive the transformer into saturation and ultimately into what they call an overfluxing situation, which is not healthy for a transformer. So keep in mind that voltages vary as the changing flux, or voltage varies as delta flux, if you want to call it that, and current is proportional to flux. These are two concepts that you have to keep in mind anytime you're doing analysis. Sometimes you lose track of that, but the voltage varies as the changing flux, and the current changes with the flux. With the load connected across the terminals of the secondary winding, the circuit on the secondary side of the transformer, of course, is complete, and a current I2 starts to flow through it. The magnemotive force corresponding to the current on the secondary winding is given by this equation. The MMF is equal to N2 times the current in the secondary. The magnemotive force corresponding to the current in the primary winding is given by this equation. The MMF is equal to N1 times the current in the primary. The flux linking the two coils, phi, is equal because we have the same amount of flux in the primary coil as we do in the secondary coil. And the MMF, or the magnemotive force, is equal in both the primary and the secondary coils. So we can equate the top two equations. N1 I1 is equal to N2 I2. Or the ratio of the secondary current to the primary current is given by the ratio of the turns of the primary coil to the secondary coil. Remember now from previous discussions that the voltage is given, the voltage ratio of the primary to the secondary is given by the turns ratio, which is N1 all over N2, which is just the inverse as to how the currents are related. The power dissipated in the secondary load is given by the equation V2 times I2. The power coming from the primary is given by the equation V1 times I1. But the current and the voltage ratios are given by these two equations, which we just developed. So we can write the power delivered to the primary in terms of the secondary voltage and current by substituting V2 and I2 for V1 and I1. And we see that we can get rid of the turns ratio, and we're left with the fact that the power coming into the primary side is equal to the power going out the secondary side. So this should be no surprise. You can't create power, and the transformation of the voltage and the current should take that into consideration, which you can see here it does. When a voltage is applied to the primary of a transformer and a load is applied on the secondary, a voltage appears across the load according to Faraday's law. The current in the secondary will therefore be determined by the impedance of the load, which we have labeled Z2 here. And the current can be calculated, of course, by using just Ohm's law, which is I2 is given by V2 all over the impedance of the secondary load. But I1 is equal to N2 over N1 times I2. If we let Z1 represent the secondary load reflected onto the primary load, because now the current on the primary will adjust itself depending on what the load on the secondary is. Well, we're going to find out how it does that right now. We do know that Z1 is equal to V1 over I1. Now, if we substitute the secondary voltage and current for the primary voltage and current, we get this equation, which seems to be very cumbersome. We can rewrite it, just bringing everything down to the to where we have only one fraction line, and we see that the impedance reflected to the primary side of the transformer is given by Z2 multiplied by the square of the turns ratio. This is characteristic of a transformer, and it becomes very handy for impedance matching and the like, which you have to do sometimes in audio circuits. However, if you are going to see what the impedance reflected to the primary of a transformer is, you have to use the square of the turns ratio. This ends the video on transformer fundamentals.